Professor Leo C. has a joint appointment in the Department of Computer Science and Statistics here at Purdue. His research includes information retrieval, applied machine learning techniques, and text mining techniques for different applications. And even though he is a fairly young assistant professor, he already has over 80 publications. He is a recipient of a career award from NSF in 2008, and he served as area chairs for conferences such as SIGIR, WWW, and CIKM. He received his degree in computer science from Carnegie Mellon University in 2006. I already took a lot of your time. Please.
Thanks. Can you hear me? Okay. Can you hear me better? Okay, thanks. So again, welcome to Purdue. And it's already pretty late in the afternoon. As Sergey said, it's good that I do not have so much math or so many math formulas in my slides, so that you will relax a little bit, and we will discuss that how we can apply some learning techniques to the application of information retrieval. So today, well, okay. Today, I would like to talk about a machine learning approach for information retrieval applications. So you guys have learned a lot of great learning techniques in the last few days, and I would like to take the opportunity to share with you guys some of our experience for designing and developing learning techniques for the information retrieval applications. First of all, let's talk about what is information retrieval and why we need these information retrieval techniques. So since the introduction of the World Wide Web and the digital libraries, people has accumulated a huge amount of digital information. So this figure shows the number of websites on internet. If you are lucky enough, you create a website in 1993, your website is among one of the top 100. But look at today, we have exponential growth of the contents on the internet. And now we have close to 1 billion websites, or even more today. So therefore, we have a big problem of information overloading. And we need to find out useful information among huge amount of digital information. So there are some study which has been done in year 2008 that measures how much information Americans consume in their daily life. So I want talk about the specific numbers, but from this big trillion, from this big bet, you can tell people consume huge amount of information. And also people consume information from different sources. For example, traditional media like newspaper, like book, and also as well as these days from social network, from the World Web, so on and so forth. So therefore, we have too much information. And we would like to identify some techniques that can better help us to find useful information, to utilize useful information. And so therefore, a group of people, I think, in computer science start to do research information retrieval a long time ago. But this community gets much bigger in the last 20 years because of the WWW. And in the narrow sense, information retrieval ranks a collection of documents for user queries according to the degree of relevance of user query to the available documents or web pages. So in this sense, you know that this is a definition, for example, for the web search, which all of us have been using in a daily manner. But in a broader sense, information retrieval techniques provide a solution of acquisition, storage, analyze, organization of, and analysis of information. So this sense is pretty broad, and we are going to talk about some specific applications to achieve those goals. And in particular, information retrieval techniques mainly study unstructured data. This is different from some of you guys may be familiar with relational database management, where you have a well-defined schemas on your data, so you have access to well-structured data. But in information retrieval, most of the data are in unstructured format. So for example, text in web pages, images, audios, even protein sequence, so on and so forth. And if I'm only allowed to talk about one application in information retrieval, the most visible one is web search, which was one of the biggest things in the last 2 decades. However, we have a bunch of other applications beside web search. So for example, we may want to do information organization. People have a huge amount of information, and we would like to organize them in different meaningful ways so that user can access them in a convenient manner. And we have a text categorization, we have a document clustering techniques, which are 2 of the most well-known examples in machine learning techniques as supervised learning and unsupervised learning. And we also have an information recommendation. These days, recommendation has become a very popular technique in different e-commerce applications. I assume most of you guys know the Netflix computation, which designs recommendation algorithms for movie recommendation. Actually, tomorrow, in the first student lab sessions, you will have a chance to have some hands-on experience for developing some simple recommendation systems. And we also do information extraction. That means we want to go beyond web search. Web search only returns a bunch of documents with respect to user query, but doesn't do any type of deeper analysis. For information extraction, we want to get a deeper understanding that goes beyond the surface text data. We may want to know who are the people mentioned in this text document. What are the organizations mentioned in this text document, and what are their relationships? This belongs to the application of information extraction. And another very visible application these days is question answering. How many of you guys have heard about this IBM Jeopardy deep question answering system? That's good. Many of you guys have heard about it. So in this case, we would like to go beyond identifying documents for users, and they have to look through the documents by themselves. We want to directly answer the question posed by user query. And that's the application of question answering. So we also have another search paradigm, which is different from the general common commercialization search paradigm like Google or like Microsoft Bing. This is called federated search, which will enable us to explore a large amount of hidden web contents. I will elaborate a little bit more later about this application. And also, we have a multimedia information retrieval for images, videos. And I think Professor Ramani probably yesterday talked about something about shape retrieval. That is another example of multimedia retrieval tasks. So on and so forth. So in these days, I view that information retrieval is a research community that can really generate a lot of interesting and practical applications. That's the power of this community, because web users or general users always pushes new applications towards. So I would like to talk about some of the specific applications, but our group has done some work for this set of applications. Well, I will only have time to talk about a couple of them. So information retrieval can be viewed as a cross-disciplinary community that connects many different research communities. For example, we utilize the theories from machine learning community. we utilize theories from natural language processing community, and then we utilize them in 2 different applications. In particular, I think the most important techniques that information retrieval people or IR people utilize are the machine learning techniques and the natural language processing techniques. But in this talk, I will mainly focus about some machine learning techniques that has been utilized for information retrieval applications. So we know that there are a bunch of applications in IR community. And I would like to only talk about one specific application to talk about some valuable previous research. This is called ad hoc retrieval. And actually, web search is a specific example for the ad hoc search task. Basically, this means that we have a user query which generally poses in text data, representing users' information need. And those user queries are generally short and represent the temporary needs. For example, like information about current movies, so on and so forth. Well, the user queries are dynamic, but information sources are generally relatively static. So in these cases, we want to look for relevant information in the static information source to satisfy a user's query. And there are some examples about ad hoc search, such as web search, library search, entity search, which is getting popular recently, that's trying to identify important entities, like people, organization, and relationships from available web contents. So I would like to spend a little bit of time to talk about the previous research in the IR community on ad hoc information retrieval or the ad hoc search task. On the left-hand side, we have a bunch of intuitive algorithms that are designed based on calculating similarities between user query and available document information. So this is very simple. We want to represent user query and available documents in the same vector space, calculate their similarity, and we will just return the most similar documents back to the user. So one of the most popular example is this vector space model. I'm going to elaborate a little bit. This was designed almost 40 years, almost 40 years ago. And this type of model is very intuitive, we are going to see. However, it doesn't enjoy very good solid foundation, and it depends on a lot of heuristic choices. So later, the researchers in the IR community goes a step further to design more complicated and more effective probabilistic information retrieval approaches. And in particular, one approach is based on the generative model, which means we want to calculate, given the available documents, such as web page, what is the probability that given the content of this web page, we can generate a user query. And this is called a generative model in the information retrieval community. And more recently, more and more people start to work on discriminative model. This means we actually don't care how the query is generated. What I really care is, given a pair of a user query and let's say a web page, whether this web page is relevant to the user query or not. So in this case, we want to calculate the conditional probability of being relevant given the pair of user query and web page. This falls into the discriminative model approach. And in particular, this has aroused a lot of valuable research recently called learning to rank. So I would like to elaborate a little bit of these 3 approaches: vector space model, the generative language modeling approach, and also the discriminative learning to rank approach. So first of all, the vector space model. As I mentioned, we would like to represent user query and available documents, or web pages in this case, in a unified vector space. So for example, we may utilize the individual keywords as the dimensions in this vector space. and we're calculating some type of weighting schema for representing all of the documents, as well as the user query in this vector space. And after we have the vector representation, we will be able to calculate the similarity between user query and available documents, and then eventually we will retain the most similar documents with respect to user query. So this is intuitive, and this is very effective actually in some sense, especially for the first generation web search engines. I do not know whether you are old enough to know Alta Vista or Lycos. Probably not. I'm too old. So those first generation search engine, actually, most of them are based on this type of vector space model. And the two very important concepts introduced by vector space model are term frequency and inverse term frequency. And especially the inverse term frequency is very intuitive. This means we want to detect the most useful or most important query term in user query. Let's say if a collection is a Wall Street Journal about business articles, and user query is a Brazil market. Only two words, Brazil and the market. So if I ask you which word is more important for this Wall Street Journal connection, can you tell me which one is more important? Brazil, right. So basically, the inverse term frequency captures this kind of behavior. It looks like which term is more rare in the collection, and a rare term tends to be more important than a more common term. And that's denoted by the inverse term frequency statistic. So this is very intuitive. Actually, a lot of people has done some interesting research to show how inverse term frequency or inverse document frequency, that's another name for this word, related with the smoothing techniques, such as Dirichlet smoothing or linear smoothing, so on and so forth. So this is the vector space retrieval model. It's good, it's intuitive, and it works. But it depends a lot of heuristic choices, such as how to define the weighting schema. And also, it doesn't have a solid foundation for example, like the document representation. And another major disadvantage of this is it's difficult to incorporate some type of complex features. So for example, like the page rank features. Page rank is an important statistic used by second generation web search engines like Google to indicate the importance of a website by looking at its link structure on the internet. So because the vector space wants to represent everything in the vector space, it's not that straightforward or coherent to incorporate these features into the vector space model. So therefore, people want to go a step further. And in particular, they want to find some type of representation that has better or enjoys a little bit more solid representation. And this type of statistical language modeling approach has been a very popular approach in the IR community in the last 10 years. And the idea is also very simple. So basically, it means we want to model a document or a query as long as a bag of words a representation. So we are assuming that this model is a multinomial distribution. So therefore, given each word or each query, a term, we will be able to generate this word or query term from this multinomial distribution. So the approach is we first learn this multinomial distribution for each document, and then we calculate the generation probability of user query given the language models of all those documents, and then we return the document that is associated with the highest generation probability. So the idea is very simple. The basic idea, we estimate the document language model, and this document language model is generally smoothed based on a larger collection of documents, because we would like to consider the data sparseness problem in short documents to consider a larger context. And one type of smoothing is this type of linear smoothing that, that can extend the MLE, maximum likelihood estimation of this document language model. So this is one popular approach in the IR community, but it does have a better, more solid foundation than the vector space model. However, on the other side, it's also not able to incorporate more complex features, for example, like PageRank. Because in the statistical language modeling approach, it makes a big assumption that the document models is a multinomial distribution. And if you want to incorporate another type of features into the framework, and in particular, if you want to tell a coherent story, you want to incorporate this into the generation process. But this is not easy to do with arbitrary type of features like the PageRank or other type of features. So that's why more recently, in the last 7 or 8 years, more and more people start to utilize discriminative models. Or more particular, the learning to rank approach is getting more popular these days. What this means? This means we really do not care whether a user query can be generated with the highest probability. What we really care is given the user query and the document to estimate whether this pair of query and the documents, they are relevant with each other. So what this method does is, it designs a different type of feature functions given a user query and the document. You may imagine some features may be the number of overlap words in the documents and in the user query, and some other features that incorporate the IDF or ITF features into it. And there has been a lot of study on what are the effective features. There's some popular research being conducted by Microsoft Research, which designs more than 100 features. And one simply modeling approach to utilize these features, what about we just throw them into a simple logistic regression model, so that we want to calculate the weight associated with each feature. And using this model, by learning this model on some training queries where we know the relevance judgment, we will be able to build this type of a simple model. And then given a new user query, we will be able to tell the probability of relevance for all of the documents. And then we can return the documents by sorting through or by sorting on the probability of relevance. So this idea is very simple, and, but it really works. Actually, one thing which is good for this is this type of model, actually a little bit more sophisticated model, has been really utilized in commercial search engines like Microsoft Bing. You may have noticed that the improvement of Microsoft Bing in the last maybe 1.5 years, actually a major part of that comes from utilizing this type of learning to rank algorithms. So this is better. And this better in the sense that it can explicitly optimize the retrieval performance or in a discriminative way by the set of training data. It provides a solid foundation for modeling relevance, which is better a step further than the generation probability. And it has been used in many commercial search engines. And in the last 5 years, people have extended this simple idea to more complicated situations. So for example, in a lot of cases, we may not be able to know what are the really relevant documents. In a lot of cases, what users give us are some type of implicit feedback. So you go to Google, you go to Microsoft Bing. You will never tell, or they even don't bother you to give them label whether this document or this web page is relevant or not, right? What you do is, maybe the first one is not good. You skip that, but you click on the second one. And then the third one is not good. You click on the first one. So this type of behavior or implicit feedback cannot be modeled by the binary concept of relevance. But on the other side, you may model this in a little bit smarter way, which means you click on the second, you ignore the first. That most probably indicate that for you, the second one is better than the first one, right? So people try to, or those commercial search engines try to utilize this type of behavior and to model the data in the pairwise situation. That means, given user query and a pair of web pages, we will be able to determine which one is better or is more relevant than the other one. This is a pairwise approach. And also, people go a step further. What about we just consider the whole list instead of besides a pair of documents? And there have been some nice research that has been done for list post approach. There has been some nice, actually, theoretical study that theoretically shows that the list-wise approach in the symptotic sense is better than the pairwise or the point-wise approach. But a lot of most empirical study shows pairwise approach is generally more effective than the point-wise approach, which is the logistic regression model we talked about in the last slide. Well, the list-wise approach only have a very small margin improvement. So we have seen that machine learning techniques can help information retrieval applications in the case of ad hoc search. And our question is, can the success of those machine learning approach be generalized for the ad hoc retrieval to other applications, to the applications I mentioned on a few slides earlier? And definitely the answer should be yes. Otherwise, I will not give a talk here. But this requires us, we need to figure out some specific requirement about learning algorithms for designing different complex information retrieval applications. And I will only elaborate 3 applications, and I will show some of the modeling techniques we have been utilized for those 3 applications. But similar techniques can be utilized in many other IR applications. The first one is question answering. So this means we want to identify the answer to user query directly. And let's say the question is, what is the city in China with the largest population? So the system is pretty complicated. In the first step, we want to extract important keywords about user questions. In this sense, this may be city, China, largest population. And then we do retrieval. We get back a bunch of relevant documents. And after that, we utilize some answer extractors to extract possible answers or answer candidates from the relevant documents. And the final step, which is one of the most important steps, is answer selection. We want to select the most useful answers from the candidates as the answers to user questions. So this is question answering. I'm going to talk about that. And the second application I would like to elaborate a little bit is a federated search. So every one of us utilize web search engines. But actually, web search engines only represent a part of the accessible information on the internet or on the general digital world. A lot of information in some information sources cannot be arbitrarily copied or crawled by commercial search engines like Google. On the other side, they create their own search engines so that information are staying behind their own search engines. There are a lot of examples, so for example, like digital libraries. And in these cases, we have to solve the search problem when the information is physically distributed across different information sources. So here, we are assuming information is distributed across a bunch of information sources. And in the first step of the search process, we need to figure out what kind of contents each information source contains. One digital library may be about a scientific publication. The other may be about biomedical. The third one may be economical, so on and so forth. And then with the user query, we need to do an important task here is to select a few most relevant information sources to search. Because in general, in a lot of real-world applications, so for example, we are building a system for PURDUE library, which accesses 400 digital libraries. We cannot afford to send user query to all of these digital libraries. We can only afford to search some of the most relevant ones for each user query. And this step is called resource selection. And after that, we will be able to get return the results from the information sources, the selected sources, and merge them into a final list. In this talk, I'm going to elaborate a little bit on one resource selection or the source selection algorithm we design. And the last application I would like to talk about is expertise search. So in the information age, the most important thing may not be what you know, but who you know. So in these cases, expertise search aims at finding the right people with the desired expertise, and we want to search people instead of documents in these cases. And in the real examples, as real-world systems we have built, each expert candidate is associated with information from heterogeneous sources. So for example, a faculty member at Purdue has web pages, he has some publications, he has a bunch of research projects, so on and so forth, and maybe supervised PhD dissertation, so on and so forth. So we need to figure out the expertise information from the heterogeneous sources and to test out whether the information satisfies user query or not. So in this case, we have to face a problem how to integrate information from heterogeneous information sources. And I'm going to talk about that. So I would like to address particularly three issues that we have designed some learning algorithms for the IR applications. The first one is we want to break the isolated information items to consider a joint set of information items. So as the case for the web search, one approach is look at each document or each pair of a document separately. This is okay, but it may not be optimal. Because in a lot of cases, those information items have a relationship. So for example, if one web page has a connection to another web page, and both of them appears on the list, if we are pretty sure that one of the documents is relevant, then the other document or web pages also tends to be relevant. So in these cases, we want to go beyond the isolated information item, but consider a set of items in a joint way. And in particular, this is the case, for example, for question answering, where we would like to select answers. And we are going to see how we model this in a joint manner so that we can improve answer accuracy as well as to reduce answer redundancy. And this is also the case for faculty search, where we have to select relevant information sources for user query. And if we know some of the digital libraries, they have a relationship. So for example, one digital library may have a lot of articles refer to the articles in another digital library, then we will be in a better position to model them in a joint way to improve the ranking accuracy. So our approach is we would like to see how we design a joint probabilistic approach that can model available information items as well as their relationship. The second thing is, in a lot of information retrieval applications, we do not have complete supervised information, like, for example, for text categorization, where we always assume that we have a bunch of training documents. We know their labels in a perfect way. But in a lot of cases, this may not be correct. For example, in expertise search, if I give you a bunch of training data for expertise search, that generates in this form. I tell you for a query, who are the experts for this topic? Let's say computer security. But in the real world case, as I mentioned, that each expert is associated with information from heterogeneous sources. And the people, for example, he may have 10 research projects, 120 publications, 30 supervised PhD dissertations. And a lot of researchers actually are working in different ways. And also, the contribution of experts in a publication may be in different way. For example, a lot of people let's say, in enterprise, they may be involved in email connection, in email discussions. And in some cases, when one employee is discussing some technical issues with another employee, he may just CC this email to his boss, who may not actually have a technical expertise in this area. So in this case, we only know the overall relationship about who is the expert in this topic. But we do not know which particular document, which particular email, which particular publication actually represent this expert's expertise. Some of the documents belong to this expertise this expert may not be relevant to this topic at all. So in this case, we are going to introduce our integrated learning approach that explicitly models incomplete knowledge in the training data. And the last one is how to combine the evidence of information items from heterogeneous sources. Again, this is related with the example about expert research. We have information that for an expert from heterogeneous sources. How can we combine them together in a nice way? So for example, when we designed the real-world system, we encountered a lot of examples like this. We use web pages, home pages as evidence for expert candidate. But a lot of senior faculties, for example, distinguished professors, they don't bother to update their web page. They only have a contact information on their web page. Or they even do not have their web pages. In this case, we may not want to simply downgrade the expertise of these people because of this. And another example is a lot of young or new faculty members, they may not have time to graduate PhD students yet. So if they have been at university for 2 or 3 years, maybe he doesn't have a supervised PhD dissertation. But this doesn't mean he is not good in his area, right? Because he simply do not have time to do that. In those cases, we should also consider what type of expert candidate is in order to integrate information from the heterogeneous sources. So by doing that, we are going to see that we design a mixture mixture probabilistic model approach that can integrate information from heterogeneous sources by intelligently learn the weight of different information sources given an expert and a particular user query. So let's look at these 3 problems and our corresponding approach for addressing these issues in the real-world information retrieval applications. The first one is answer question for answer selection in question answering. There has been some valuable previous research in this topic. For example, there are some research that utilize independent classification models, just a logistic regression model, given a user question and answer candidate, extract features, predict whether this candidate is relevant to user question or not. This is the independent classification model. But our argument is we want to model the relevance of individual answers and their relationship together in a unified way. Yeah, because this is like that. If 2 answers, they are somehow similar with each other. So for example, if you know from WordNet, these 2 words are synonyms or somehow related. And if you know one answer may be highly relevant, then the other answer may also tends to be relevant. And we would like to model this kind of behavior. So basically, what we designed is like that. We want to learn the set of relevance output, which is indicated by the vector S here. They denote the relevance judgment for all answers, and we would like to learn them in a joint way. So our joint classification model is we want to predict the set of answers, vector of answer S, given the feature F here. Feature is the set of feature that consider user query and answers in the individual way, as well as their relationship. So as I mentioned, that we have 2 components. The first one models the relevance of individual answers. This part tells us how probable an answer is by itself. But on the other side, we also consider the relationship between the answer candidates. So for example, whether the spelling of these answers are very similar to each other. That's one type of relationship. Another type of relationship is whether they are synonyms or they are related with each other in WordNet or other type of dictionaries. And we learn this model in a joint way, in a unified framework. So we believe this is a better approach than ignoring the second part, but only modeling the first part. So this type of model actually has been utilized in machine learning community or started in the learning community for a long time. not only in a learning community, but it has a long history back in the statistic mechanic community. And some of the alternative names are Boltzmann machine or the Ising model. So by learning this joint probabilistic distribution, what we can do is we will be able to tell the marginal probability distribution that tells us whether a specific answer is relevant or not. Please note here, this is the marginal probability from the joint probability, which is different from the individual probability that only considered the information for this particular answer. And another nice thing from this is we will also be able to consider another item here. The second item actually tells us we not only want to know the relevance for each individual answer, we also want to know the relationship between the answers. Because by the end of the day, you want to get good answers. Your answers should be both relevant and unique. You do not want to see duplicated answers, 20 duplicated answers, right? So the second part will utilize the conditional probability here that can help us to remove a redundancy. This may be a little bit abstract, but I would like to give one example here. Let's say that we will be able to learn the probability the model, and we can utilize the model to answer the question, who was the US president in the 1990s? And let's say we have three answer candidates. The first one is Bill Clinton, and this has a high probability of 0. Actually, William Clinton, which has high probability of 0.8. And the second one is Bill Clinton, and this also has pretty high probability, which is 0.7. Well, the last one is George Bush, has a little bit lower probability of 0.6. And what we can utilize the joint model is, we will select the first one, because at this time we do not have any duplicated answers. We will go ahead and select the first one. But for the second one, we will be able to calculate a new score of this answer. The first part of this new score represents the probability of relevance, the marginal probability of relevance. And the second component represents the conditional probability that considers the already selected answers. Because the conditional probability between Bill Clinton and William Clinton is they are very similar. So that's why this conditional probability is high. And then we can calculate a new score for this answer. And in a similar way, we can also calculate a new score for the third answer, George W. Bush. And eventually, we will be able to select these two answers by their new scores, and we will be able to ignore the second, which is duplicated answer, and we will be able to select the third one. So this shows some of the power of our joint probabilistic approach for answer selection. And we did some study about the empirical study about this new approach. When consider a baseline, previous state-of-art approach, a baseline approach in the question answering community, we compare this joint probability model with the independent probability model on two data sets with two types of information extractor, and it shows a relatively good performance. It improves the previous state-of-art results. So the math detail about how we do inference, how we do learning here, and also the empirical details is in our paper, which I will give a reference by the end of this talk. So we have learned how to utilize this joint probabilistic model for one application. And in a similar way, we can utilize for other applications. So for example, for the source selection in federated search. And in this case, our argument is we want to go beyond the evidence of each individual source, for example, like a digital library. We want to consider its individual evidence as well as the relationship between different information sources or different digital libraries. So therefore, we will be able to utilize a joint probabilistic classification approach in a similar way to jointly predict the probability of relevance for a bunch of information sources. And that's what we did, how we modeled this application, and we also have done some empirical study to show the performance on some experimental or research data set, as well as a real-world application. The last one is a real-world application for Purdue Library, which searches about 100 information sources, 100 real-world digital libraries. So this is some of our work that we have done that utilize joint probabilistic modeling for modeling information atoms together than modeling them individually. And the second thing is we want to consider incomplete knowledge in some real-world applications. So for example, in the expertise search, as we mentioned that for the training data, we only know which expert is actually related with a topic or an expert in a topic. But we do not know which documents of this expert candidate actually shows his expertise on this topic, which is also important. And so therefore, what we did is we proposed a unified model that integrates the document evidence and the document candidate association. Here, this means document evidence shows for each document whether this document is talking about contents about this particular topic, for example, like computer security. And the document author association tells us whether the particular expert candidate makes a contribution in this document. As I said, if this email message talking about computer security only CCs, let's say, the manager of a division, then this manager division, this division manager is not necessarily an expert or is not necessarily contributing to the technical part of this document. So we are going to see this unified model. Before that, I would like to point out the previous state of art of expertise search information retrieval community. And this is done by utilizing a generative probabilistic model approach. Again, this is similar to the language modeling approach for web search. Instead of modeling the generation probability of a query given a web page, it models the generation probability of a query given an expert. And what this formula shows is it looks all of the documents that in the corpus, and it models two components. The first component is the document language model that tells us the document evidence, whether this document is supporting or is talking about contents about this topic. And the second one tells us the association between the author, the candidate, and the document. And this, for example, can be modeled by some heuristic approach. Like, say, the frequency of the expert's name appears in this document, the higher, the more association between the document and the expert, so on and so forth. This actually provides a pretty strong baseline and with careful engineering tuning. However, again, the issue for this is a generative model. It has to follow this kind of generation assumptions, like multinomial distribution assumptions, so on and so forth. And it's not easy to incorporate the different type of features into this framework. And our approach is we designed a discriminative model for integrating the document evidence and the document author or document candidate association into a unified framework. What we did is, again, we do not want to model generation probability. We want to model the probability given the user and a query, what is probability that they are relevant. And we introduce two hidden variables here. The two hidden variables represented by R1 and R2. What they mean is, the first hidden variable tells us whether the document is relevant with respect to the user query. And the second hidden variable tells us whether, given this document and the expert candidate, this expert candidate is really responsible for the contents in this document. And also, we have another prior term tells us the importance of each document, which generally can be assumed in a unified way. So we model this probability in a discriminative way and also specifically introduce two hidden variables. Actually, what we do here is we throw our prior knowledge into the modeling process. what we did is, instead of modeling the conditional probability of being relevant in a big, let's say, regression model or in a big model, we throw in our prior knowledge in the structure of the model, which means we separate the document evidence part from the document candidate association part. And this is the prior knowledge, structure prior knowledge we throw into the modeling process. It reduces the model complexity, but on the other side, it generally improves the generation error, the generation accuracy, because the model is simpler. And we have done some empirical study to show the performance of that. I'm going to show a little bit later. But for these specific components of the document evidence part and the document expert association part, we can use different type of models. One simple example will be utilize logistic regression, or let's say general exponential family models for each component. And by doing that, we will be able to utilize different types of features. And here the advantage is we are not making any of this type of generation assumptions in the generative models for doing that. And we have done a study on two standard benchmark data set. One is W3C, this W3C organization. The last one is CERC, which is a research organization in Australia. And the discriminant model has been shown to have a big advantage against the generative model in this case. So the last one I would like to speed up. The last issue we have done, the problem, technical challenge for information retrieval applications is how to integrate information from heterogeneous information sources. And this is pretty interesting and a tricky problem. For example, for expert research. In our real-world expert research system, we are combining expertise information from 7 or 8 heterogeneous information sources, like homepage research project, surprise PhD dissertation, technical transfer, patent, and so on and so forth. And one question is how we can combine the information together from heterogeneous sources. One straightforward idea is like that. Let's again just use simple logistic regression, right? In the logistic regression, we assign or associate weight with each type of information source. We learn their weight by maximizing the relevance judgment on consistency of relevant judgment on a bunch of training data. And then we use this simple logistic regression model for prediction for the other things. However, our argument is this method is not optimal. We have given some examples that we believe the combination weight should depend on experts. So for example, senior faculty members may not have home pages. Some young faculty members may not have surprise PhD dissertations. Yes, in these cases, we may not want to punish them because they simply have reasons probably good reasons for not having this information. On the other side, we believe the combination should also depend on query. So for example, if the user query is a cancer treatment or cancer research, and if I say I'm the best cancer doctor in the world 100 times on my web page, I believe you still will not send your patients to me, right? Yeah. So in these cases, this means for this type of query, this particular example about cancer research, we probably would like to place a higher weight or larger weights on research projects from NIH or other type of publications instead of information on home pages. On the other side, if this is about music or some like administration positions, then information from the home page probably will be more important. So this is our intuition. Our intuition is we believe the combination should depend on not only the question, the information request, but also on what type of expert candidates we are considering. So that's the idea, or that's the foundation why we would like to design these kind of models. So again, to be simple, we want to predict the probability of relevance given an expert candidate and user query. And Our model claims like that. We believe there are different types of expert candidates and different types of information requests. And given this hidden representation of these information experts, what type they are, or what type of information request we are dealing with, then we can combine the information sources in a more elegant way. So for example, as we said, for the case of young faculty members, we may not put too much weight on the supra-SPT dissertation. For the query like cancer treatment, we may not want to put too much weight on the, let's say, homepage, but we want to put more weight on projects from National Institute of Health, so on and so forth. So here we have one component here that tells us what is the latent variable or the latent class of an expert candidate by looking at a bunch of features of this candidate. And we have another latent variable that tells us what type of user query is about. And then based on these two hidden variables, we combine the information sources together to predict whether an expert candidate is really an expert for a user query. So there's some math details here. So for example, how we do inference. This is straightforward expectation maximization algorithm. If we do, this was also made a little bit fancier. So for example, we can automatically build the topics of queries not only by the pure discriminant learning, but a combination of discriminative and generative learning. And some of these details is in our paper. So we have done some experiments on our new model. This is on a real-world example for state of Indiana. And we compared a couple of algorithms. One of the algorithms is called compound sum, which is a very popular algorithm if you are in information retrieval or knowledge management community. And the other baseline algorithm is this single logistic regression, which learns a set of fixed ways. And finally, our mixture model that learns the adaptive ways for different types of user queries, and also information needs. And this shows the results. The new approach is better. So that's all. I mean, we have talked about, we do not have much time, so I only talk about a few issues emerged from real-world IR applications, like how to model information items jointly, how to work with incomplete knowledge, and how to do information integration from heterogeneous information sources. And this shows a little bit, a few references for some of the work I mentioned. And finally, I would like to thank my student collaborators, and some of them actually are sitting here, and also my collaborators from Purdue University, from Google, and from Carnegie Mellon University. And I would also thank some of the funding agencies that have supported our research work. Yeah, that's all. Questions?
Before we take a few questions, I would like to remind you that we're going to take a picture immediately after, at the end of this talk. If you have a couple of questions for Dr. C,
right.
Go ahead.
Yeah, maybe I talked too quickly. I talk too much. It's difficult to find. But if you have any question, I will be around, so you can also ask me offline. Okay, thank you. Thanks.
Do you have a couple of minutes to take a picture?
Sure, sure, yeah.
We're going to go across.